Um, Good afternoon, everyone, and welcome to the last day of the webinar. Today, we will continue with methods to combine uncertainties. The last 2 days, we've learned how to apply approach 1 and approach 2. And now we will learn how to combine both approaches for uncertainty analysis. Then the next item would be application of uncertainty estimates to identify areas for improvement, approach 2 to identify key categories. This session will explain how the results of the uncertainty analysis are used in approach 2 to identify key categories and prioritize activities to improve the inventory quality. Then we will cover the last technical agenda item of the webinar, which is uncertainty associated with the use of proxy, splicing techniques, and expert judgment to fill data gaps. As you know, data gaps are common issues are reported by developing countries, and the session will analyze how the use of proxy, splicing techniques, and expert judgment can introduce uncertainty and how this uncertainty can be quantified. Then we will close the webinar. So we have a lot to do today, and I hope, Diego, that we'll be able to cover all these elements. So let's start right away. Good participation to everyone. And once again, please focus on the technical content of the presentations. So Diego, I hand over to you.
Hello?
I can hear you, Diego.
Thank you. Hi, Savan. Thank you for the introduction for the last day of the webinar. Welcome to you all for this last session. Thank you for being happy Friday for everybody. And thank you for being today and bearing with me during the whole week. I really appreciate the time you are taking to take this 2 hours during the whole week. And I hope you are learning something at least from today's, that you learn something new, or you refresh something you already know. So today we will go over the last items for this webinar, as Savan just mentioned. So I will start sharing my screen so we can move to the first part of this. Let me
Yes, I can see your screen.
Great, thank you. Yeah. Okay. Good. So today we will have 3 sessions. The first 2 are quite short, I would say. It's yesterday we saw how to apply Monte Carlo simulation technique approach 2 to propagate the errors in the input data. And on Wednesday, we've seen how to propagate the uncertainties based on the linear error propagation. And we've seen the assumptions of both of the two approaches, that there were a lot of assumptions under approach one. We assume small standard deviations, we assume symmetrical distribution, normal distributions, we assume no correlation, so independent variables. And the IPCC guidelines provides us with equations for propagating additions, subtractions, and multiplications. So we use that to apply and to propagate the uncertainties. And yesterday we applied the Monte Carlo technique and we used the probability density function as the input data to generate a new probability density function of the result. And you've seen that the Monte Carlo approach may be very demanding in the type of data we require to select and build the probability density function for the parameters. So what we will see today with this hybrid combination, the hybrid approach, applying approach one and approach two, is a very useful and efficient way of improving the uncertainty accounting without unnecessary efforts, I would say, because there are some categories that are very, very well estimated and can be propagated fairly good applying linear propagation, so that using Monte Carlo simulation for those categories may not worth or maybe a waste of resources if we are having problems with limited resources, which is almost the case for all developing countries. So this hybrid technique applies a combined approach. So we will learn today how to combine the approaches and see where the efficiency comes from, which you may already understand very well. So what's the hybrid approach? It's just combining the two approaches and apply it for the categories that really require a higher approach or more detailed approach, or where the assumptions are not met or are very different from the real assumptions, because there are some categories that do not match the assumptions for linear error propagation, but they are not so bad. I mean, the uncertainty may not be very small, but it's not so high, or there may be some correlation, but it's weak, or there may be some asymmetry, but the asymmetry is small. So for all those categories that do not fully comply with the assumptions for linear error propagation, we can still apply approach one, linear error propagation, and we will get good results anyway. So for those categories, we may still keep the linear error propagation approach. So the idea is to identify which of the categories are really not complying with the assumptions of approach one, but with high differences, big, large uncertainties like 100% uncertainty, or very, very asymmetric cases, or really strong correlation between some of the variables, things like that, that justify moving to approach two. So we can select those categories in particular, and we could run the Monte Carlo simulation for those categories. We can arrive to the uncertainty for those categories at the aggregation level we need. And then we run approach one, linear error propagation, for the rest of the categories, and we combine the resulting uncertainty for all the categories, probably using linear error propagation if we are just adding all the emission sources. So this is what we would look like a result of a GHG inventory if we apply this hybrid combination. We may have categories where we apply linear error propagation. Most of the categories will work fairly well with linear error propagation. So we may have the propagation of the uncertainty for those categories, and we will have the result of them applying linear error propagations, but we may have for some of them the entire category, a portion of the subcategory, depending on the category level you are assessing the uncertainty. Category level, I mean, like sector 1 energy would be the first level, 1A or 1B, would be the second level, 1A1, 1A2, 1A3, 1A4 would be the third level of this aggregation. So we may do this combined approach at the level of aggregation it's needed, depending on how we aggregate or disaggregate the categories, depending on the data we are using to calculate the emissions. So it may happen that you apply an approach to a second level of aggregation, a third level of aggregation, a fourth level of aggregation, just to a portion or just for one gas. You may apply Monte Carlo for nitrous oxide and not for CO2. You may apply Monte Carlo approach, for instance, in this example. The Monte Carlo approach was applied for deriving the emission factor for the fugitive emissions from solid fuels. So you may apply a Monte Carlo approach to derive the emission factor for that fugitive emissions. And then you just combine the activity data uncertainty and the emission factor uncertainty propagated with linear error propagation technique. So that's the basic idea. It's very simple. It's quite easy to understand. So you just select which are the categories that really requires applying Monte Carlo approach. For instance, in the second sector, in industrial processes and product use, this example shows that the emission factor for the cement production was derived from Monte Carlo approach, the emission factor for iron and steel production, and the emission factor for aluminium. We did this case as a hands-on exercise a few days ago. So that was one example we did by deriving the emission factor from an aluminium production facility and deriving the uncertainty associated to that emission factor. So from that point onwards, if we do that, we did that by applying statistical analysis. But we may do that and derive the uncertainty based on a Monte Carlo approach, a Monte Carlo simulation of the production facility, and derive the uncertainty based on that. And then we can just apply the uncertainty we obtained for that emission factor and just keep applying linear error propagation for the rest of the categories. So in this case, in this third sector, the AFOLU, forestation, and other land use, this example shows that the Monte Carlo approach was applied to some categories in particular, not just for emission factors. The category in its third level of aggregation, the emissions were calculated and the uncertainty was propagated by applying the Monte Carlo simulation approach. The methane emissions resulting from enteric fermentation in cattle and dairy cattle, the nitrous oxide emissions for manure management, and nitrous oxide emissions from managed soils and direct and indirect. So the five categories that are in green, they were all assessed by applying Monte Carlo simulation, because those categories have some parameters that were not really complying with the assumptions in linear error propagation, particularly N2O emissions in generally have large uncertainties and very asymmetric, and the enteric fermentation and manure management in general also have some large, or may have some large uncertainties, depending on the data we are using, and the emission factors and the tier, of course, we are applying. So in this case, for those categories, the Monte Carlo approach was applied to derive the uncertainty, and then they were combined all together with linear error propagation. And something similar happened with the fourth sector, waste sector, in which the Monte Carlo simulation was applied to the solid waste disposal, like landfills and anaerobic decay and the humidity, the decay rate. You remember that when we saw the linear error propagation approach, we did an example of the anaerobic decay of waste in a landfill, for instance. We derived the formula for linear error propagation, so we could have used that formula to propagate the uncertainty, but in this case we didn't. We just applied Monte Carlo simulation to derive the uncertainty of how methane is produced from the anaerobic decomposition of the solid waste that is disposed of in landfills or other disposal sites. And the remaining categories were just propagated, the uncertainty was just propagated with linear error propagation. I will go back to the chat. I see a question. Why Monte Carlo approach is being used for cement if the uncertainty is only 3%? Could you repeat the explanation of that example? Sure, I can go back. Here, the resulting uncertainty for the sector was 3%. That's the result of the assessment. But the input data we are using for that, depending on each statistics, if I remember correctly, when you apply IPCC guidelines for calculating cement emissions, you may calculate under tier 2 and under tier 1 based on the amount of cement produced. Under tier 2, I think it was based on the clinker production. And under tier 3, you go to the specific parameters of the plants in the country producing the cement. So depending on the data you are using, you may need an emission factor linked to the cement produced, an emission factor linked to the clinker produced. So in this case, we derive the emission factor in particular from some data, and due to the data we had, we saw that it would be good to have an emission factor assessment of the uncertainty, for that emission factor, applying Monte Carlo simulation because of the type of data we were dealing with, not because of the resulting uncertainty. Then we saw that it had 3% of uncertainty, so there may be a case in the future that we realize that it's not needed to apply a Monte Carlo simulation, or if we get better data for the emission factor, we can just apply some different value and not to apply Monte Carlo simulation for that emission factor in particular. But that's just an example, and it depends on each country's statistics, access to data, and availability of information for each of the categories. It's your call. You decide where you feel you need to apply approach 2 because you have few data, it's very uncertain, the uncertainty is high, you expect it to be very asymmetric. When you see something that clearly do not match the assumptions for approach 1, it's good practice to either get better information or to assess the uncertainty based on approach 2. So once we've done this combined approach, we then just combine all the uncertainties for all the sectors using linear error propagation, and we combine each sector uncertainty to derive the total uncertainty in the national GHG inventory. That's the way that this hybrid approach works. It's just nothing new. It's just combining what we saw yesterday and the day before. One thing that is good practice with propagation of uncertainty, either under approach 1 and approach 2, it's good if you apply approach 2, it's good practice also to try to apply approach 1. So you have a tool to see if it's worth applying approach 2 or not. Because if you apply the two approaches and you see that the results are pretty similar, you may just decide, okay, I did the exercise and it resulted, it's not needed to move to approach 2, so I can keep using approach 1 for that category. Or if you apply approach 2 and then you apply approach 1 to the same category and you see that there are significant differences in the results, then that's a red flag to see. One thing may be that it really happened that approach 1 provides poor results, so approach 2 is much better, but it may also mean that you're making something wrong or there may be a mistake. So in general, it depends on each case. It's case-by-case assessment, but when you see differences, it's good to not just to keep with that value and that's it, just to dig a little into the difference, try to understand if the difference are because of the skewness, like because of the asymmetry, because of the high uncertainty involved, what's the reason behind the difference between the two approaches. So it's all a learning technique to improve continuously our assessment. So that's the end of session 9. It's pretty simple, but it helps a lot with stagnating resources and efforts to do a good uncertainty assessment without unnecessary efforts that do not provide better results or do not improve the results significantly. So we will move now to session 10. It's another way to use the uncertainty results to identify categories that require further attention. So we will see now how the uncertainty estimates can be used to identify key categories. And we'll learn how to do that. And we will see why it's good and why it may help us with efficiency in our improvement cycles. So IPCC guidelines provides 2 approaches for deriving key category, for performing the key category uncertainty assessment. This is You can see and read the details in the Volume 1, Chapter 4 of 2006 IPCC guidelines. Approach 1 derives the key categories based on their level, on the magnitude of the emissions of each category. Approach 2 identifies key categories based on their uncertainty or the contribution of the uncertainty in the category to the total uncertainty of the inventory. So on approach 1, which is the most commonly used approach, we just want to identify the categories that contribute the most to the total value of the inventory. So the larger emissions. So we can see where the hotspots are in our national GHG inventory, and that's very useful to identify mitigation options. So the idea of the inventory ultimately is not just to get the accounting of the emissions, it's to understand where emissions are, what are the drivers, and try to change things and implement changes in the country to reduce the emissions. And to do that, it's good to put the efforts in those emissions that are larger. So we can be efficient when trying to reduce the emissions. That's the objective of a national GHG inventory. And under approach 1, we identify key categories looking at that portion of the information. Approach 1 has a different focus. The idea is to identify the categories that contribute most to the total uncertainty. Because even if the category is not so large, the emissions of the category is not so large, if the uncertainty associated to that category is large, it means that this category may be more important than we think. So the idea with this approach is to identify, again, which are the hotspots to improve the accounting of the emissions, how to improve the data collection, how to improve the understanding of those categories to try to reduce the associated uncertainty. So the focus in approach 1 is to identify large categories so we can implement mitigation activities. And under approach 2, the idea is to identify categories with larger uncertainties, or that which uncertainties have a larger impact into the results, so we can assign resources for the improvement of the accounting. These are the two equations in the two approaches. The equation in approach 1, it's very, very straightforward. You see just the amount, the emissions for each category in relation to the total emissions in the GHG inventory. And I want to make some note here, because there were a few questions in previous days related to using absolute values for the emissions or not, or how to do that. I clarified that for the uncertainty assessment, when we apply the formulas for approach 1, the linear error propagation, we do not have to apply the module, the absolute values for the individual sources. We have to just to apply the module, the absolute value of the total emissions of the inventory when we apply formula, in particular the formula related to addition. We have to apply the absolute value of the result of the addition of all the individual sources, but all the individual sources must have its own sign. If they are positive, if they are negative, they will add or they will subtract from the total. and we will apply the absolute value for the total value. That's the denominator of the formula. In the numerator, when we apply the uncertainty times the category, in that part, we have to apply absolute value, but in reality, it's not necessary because it's squared, so you will get, even if you put a negative value, you will get a positive value as a result. In this case, this changes. When we apply the key category assessment, we have to consider the absolute value of each single category. And that's why the module here, the absolute values are within the addition symbol and not outside the addition. So we do not need the absolute value of the result of the sum. We need the absolute value of each single category that we are assigning here. That's one thing that changes from what we've been doing for propagating errors. So having said that, since we now understand, this equation is very simple, and we just see in relative terms what's the weight of each category in relation to the total emissions we are accounting. Independently of if they are positive or negative, what's the size of the emissions in relation to the total value. That's the level category, key category assessment. For uncertainty, the uncertainty assessment, what we are doing, if you see the formula here, it may not be so clearly understandable because we are combining the level and the uncertainty. If you see, it's kind of weighting the uncertainty of each category. Let me use the pointer for you to better see where I'm talking to. We weight each uncertainty for each category. We weight it for its level, and we do that for each single category, and we calculate the relation of that value respect to the total of the uncertainty weight by its level. So it may not look so intuitive here, but if we add the two things, if we just put this level into this one, and we combine the two, what we see, it's, at least in my opinion, a more clear picture of what uncertainty approach to key category based on uncertainty looks like. Because when we combine the two equations, we see that what we are really doing is something very, very similar to the level equation, but instead of focusing on the emissions, we are focusing on the delta. What we are trying to see is we calculate the delta, so absolute terms, not in relative, not 5% uncertainty. We here calculate the real delta, the real value, 1,000 tons CO2 equivalent or whatever. The delta for each category in relation to the sum of the total deltas. So we are seeing the weight, how much each delta for the categories are in relation to all the delta of the categories in the inventories. So it's almost the same formula as the level approach, but based not on the emissions, but on the delta of the emissions. So let's see an example of how this is implemented. It's really quite simple. It's just following the calculations. So in general, what we will have for the key category assessment, we identify the level of aggregation we will use to identify key categories. It's good practice that if we are applying approach 1 and approach 2, we keep the same level of aggregation so we can compare the two approaches more consistently. So in general, you may all have done a key category assessment applying approach 1. So if you've done that, you will already have a list of sources with their respective emissions. You've already used the absolute value. You see here that emission source number 4 here is negative, is a carbon sink. However, when we assess the level, we apply the absolute value here. We calculate the level. We have the uncertainty of each of the categories. We multiply the level times the uncertainty, and we just derive the formula. Just the level multiplied by the uncertainty divided by the sum of all. This is exactly the same as, I will go back, applying this formula, which is the one that is shown in the table, is exactly the same. Try it on your own. It's exactly the same as calculating the deltas for each category and calculating the ratios between the delta and the sum of the deltas. It yields the same result. So this column, it's the contribution of the uncertainty for each category to the total uncertainty. And then we just rank, sort from the highest, high to low, from the highest contribution to the lowest contribution, and we accumulate the contribution up to we reach a 90% cumulative result. That's what 2006 IPCC guidelines tells us. For approach 1, for the level approach, in general, we go to 95%. In uncertainty, we go on to 90. I'm not sure, I think there are some flexibilities here to identification of key categories that may apply for some countries, for developing countries, least developed countries. There are some flexibilities here to identifying key categories assessment. So when we rank, we have a selection. We are able to identify the key categories based on the uncertainty, and we see that these 2, 6, 8, 9 categories, the ones that are pink or violet, depending on your screen, these categories are key because of their uncertainty. Then we can combine and see what happened with approach 1, and we can identify the categories that were identified as key under approach 1. Those are the ones with the green square. Those are key categories based on their level, applying approach 1. So we see there are some key categories because of their level. There are not key categories for the uncertainty. Like this, the last 2, they are important because they are high, they are large categories with large emissions, but the associated uncertainty is not that important. So we will probably not assign resources to improve the uncertainty assessment of these 2 categories, but we will apply resources to try to reduce the emissions for those categories. On the contrary, we see, for instance, emission source 6, that was not ranked as important as a key category because of its level. It's a quite small category, so it was not ranked high. It was not identified as a key category based on its level. However, you see, it's the second variable, the second source of emissions in terms of its contribution to the uncertainty. Because you can see here that the uncertainty for this category is really high, it's 100%. So in reality, what we know about this category is not that this is the emissions are 8 tons of CO2. That's not what we know. We know that this category may go from 4 to 16 based on the uncertainty. It could be double, 100% higher, or it could be half. So if it were double, 16, it would be a key category. So what we need here for this category is just to try to better understand what's happening here and try to reduce the uncertainty by getting better statistics, better activity data, better emission factors, moving to higher tiers. Perhaps this is a category that we've been applying tier 1. So we may try to move to tier 2, so to get better estimates of the activity data or the emission factors or any other parameters and try to reduce the uncertainty. So for this category, we will try to assign some resources to improve the understanding of it. Not to try to reduce it yet, because we really don't know if it's a big and important category or not, because of its uncertainty. So combining the two approaches for identifying key categories gives us a lot of information and tools to prioritize resources and assign resources for mitigation or for improving the accounting itself. I see a question in the chat. Is that very sense? In that very sense, can we say fugitive emissions from coal mines is a key category because of inherent high uncertainty involved in an estimation? It may, if you are applying a tier 1 for methane emissions from coal mines, you'll probably get a large uncertainty associated with it. Depending on the size of the emissions, if like in some countries, there are very few coal mines active. So even with large emissions, the emissions itself may be almost negligible. So probably not being part of key category under approach 2 either. But if it's a country with a lot of coal resources and a lot of coal mines, it will probably a key category based on the level and based on the uncertainty, or at least in one of the two. Okay, so that's again the end of session 10, that it's related to applying key category assessment based on the uncertainty. Let's move now. We've reached the final session 11, where we'll explore some techniques to solve data gaps, to fill data gaps, where in cases where we don't have data or where we have partial data and we have to complete the data, we will see how to apply these techniques, how to assess the uncertainty of this proxy data we are using, these estimations for those data that is missing, and we are filling with some techniques. We will see how to derive the uncertainty, and we will see how to apply or derive the uncertainty for those cases where we go to expert judgment, those situations where we have no data and we go to experts and ask for their opinion on the data itself and the uncertainty of its data. We will see some techniques, some elicitation protocols that are described in the IPCC guidelines from which we can use and apply and have that the idea is not to fully understand how these protocols work, but to understand the idea behind the questions and the approach used to get useful information, not biased from expert judgment. So for your reference, the future, this is covered under Volume 1, Chapter 5, in particular Section 5.3, called Resolving Data Gaps from 2006 IPCC guidelines. And we may have two types of data gaps. We may have data gaps that are related to periodic data. We have some publications, national statistics that are published regularly. And we may have some publications that are less frequently published than annual. So we may have biannual publications or something like that that creates some data gaps in a series. Or it's very common in developing countries for us to see some change in how statistics are published. We may have some data that was published with one technique or with one approach, and suddenly it's not published anymore, or it's published somehow differently with a different level of aggregation or something like that, that creates some information that it's not that it's not available anymore. For those cases, or for cases where the periodicity of the data is not annual, and you have to fill the data gaps, one of the most basic things we can do is, after the new data is published, we go back and see how the estimation we did changed from the real published data when it became available. So that's one of the basic things we all naturally do. The other case ends in we have changes and gaps in data, that maybe we have data from different, the statistics changes, the methodology for collecting the information changes, or for publishing the information changes, or suddenly the statistics starts applying a higher tier that was not available previously, but it becomes available from one point in time onwards. For instance, you may collect, the information for the production of an industrial product based on, a sample of the largest companies, and the statistics just extrapolate the data to the remaining sectors with some statistical approach. And then it may happen that the statistics now the agency is able to include new producers into the statistics, and there is no need for an estimation. So you are able to have disaggregated data that was not available before, or some things like that create some discrepancies between previous data and new data. So for those types of things where we need to decide if we keep using the old data, or perhaps the old data is not available anymore for the future, and you have a new data series, and you have to match the series. So we will see some techniques to try to do this, and how to assess the uncertainty for this estimate. So we will see the IPCC states 4 techniques for filling data gaps: overlap, That's when we have new data available that overlaps with existing data, but the new data is not available for earlier years. So that's overlap. When we have the same data from two different approaches that overlaps, that's one way we can create data or fill data gaps based on these relationships. Surrogate data, it's when we do not have data for one category in particular, but the category is highly correlated to another variable which we can use to derive the data of the variables we really want. So that's surrogate. When we have, in general, we do regression analysis here. Interpolation, that's when we have some data and there are missing data in between for some years, for some months, something like that. So for those cases, we can use the interpolation technique to fill those values that are missing, or extrapolation when we have some series and we don't have the last year we need. We may extrapolate the data to create an estimation of the value for the year we need the information for. I see a question here in the chat. Can you please give some examples? I guess you're referring to the data gaps. And to which magnitude of emissions a category would be key at its level. The key category based on level assessment, you have to account until 95%, if I don't remember wrong, 95% of cumulative level. That's key category. But I think there are some flexibilities for developing countries or for least developed countries to reduce that level. I don't remember if it's 90 or 85 or 80 or something like that in a cumulative basis. But the standard...
The flexibility for the key category analysis for developing countries is to use the threshold 85% instead of 95%.
Great. Thank you very much, Sabin, for the clarification.
Yeah,
so 95% is the standard threshold for key category identification based on its level. The flexibility for developing countries is reducing it to 85%. Okay, so we will go through each of these one by one to see how they work, to understand how to derive the uncertainty based on the data and based on the technique we are applying. And then we will do some exercise. We will play a little with the Excel to try to apply a few of these splicing techniques and try to assess the uncertainty associated with it. What does exactly mean higher tiers method, and why not for earlier? Higher tiers, I see Nathalie that answered. Thank you. Tier, the level of methodology you apply. When you apply IPCC guidelines, you have to choose the level at which you will apply the equations. Tier 1's, the basic level using default values from IPCC. Tier 2, it's a more sophisticated level in which you start using national values, national statistics, national emission factor, something that's related to the country in particular. And tier 3 level, it's the more complex one when you use data from each of the sources, each of the facilities, for instance, differentiating different emission factors, for instance, for each of the facilities within the country. That's typically a tier 3 level approach in the methodology. Rice area under different IPCC water regimes is available for an earlier year, which is 5-year-old data. So how do we do the data gap filling? I will read it again. Rice area under different IPCC water regimes is available for an earlier year, which is 5 years old data. So you have information from that it's 5 years old, and you need to apply it for today's national GHG inventory estimation, and you don't have the data to do that because you have information only up to 5 years old. We will see you may need to apply the extrapolation technique. We will reach there just in a few moments. Just one important note there, extrapolation may be quite challenging, not in the implementation because it's very easy, but on assessing the appropriateness of the result. Because extrapolation, it's quite dangerous. You may extrapolate whatever, but understanding if that extrapolation is a good estimate of the reality, that may be very challenging. So we may need to be very careful when we apply extrapolation technique. But just I will hold your question for a few slides until we reach there. So how we work, how we do an overlap. The idea is that, for instance, we may have a series that here you see the blue line is an existing series that we have. And for instance, the emissions, we've been applying a tier 1 approach for one category. And from one point onwards, we improve our estimates, we improve our statistic, we were able to improve the data we are using, and we were able to move to tier 2. So from one point in time here, around 1995 in this example, we were able to move to tier 2. So we may keep using tier 2, but when we want to build a series, we don't have information for tier 2 for previous years. So we may apply these overlap techniques. So instead of just using tier 1 until 1 year and then switch completely to tier 2, we can keep using tier 1 and fill the series with tier 1 and see how both series overlap. We can do that, and if we have a series of data that is overlapping the same category that is estimated with either different sources or different tiers, we may see how this relationship behave. We may calculate the ratios. This green, the gray bars shows the ratios between the two estimations, and by using these ratios, we are able to fill the data, the dotted pink line that is missing. We are able to fill this, to complete this data for previous years, even when we don't have the information to really apply tier 2 for those years. So basically what overlap does, it's the equation may look not so friendly, but it's really very simple. What you just have to do is to calculate the ratios for each year and apply the average. You know This Y are the estimations for the pink one. X are the individual estimations for tier 1. So when we calculate the ratio, each ratio for each year, we add all the ratios and we divide it by the number of overlapping years. N and M are years, in this case, we have a series that is overlapping from 1995 until 2000. So if we calculate, this is 6 years of overlapping data. So we average, in the end, we are just averaging the ratios that are overlapping, and we are applying this ratio to derive each of the new values for tier 2 for each year. If we want to understand the emissions in year 1992, we will apply the emissions, the estimate of emissions using tier 1, and we will multiply that estimation for the average ratio from the overlapping years. That's how overlapping works. Quite simple. We have to be careful with is that it provides good estimates if we see that the ratios here are kind of consistent. If we see a lot of variability in the ratios, or even worse, if we see that sometimes the ratios are positive and sometimes the ratios are negative, that may be a problem. So that may means that we may not apply overlap technique for those cases. So it requires consistent relationship between the two methods. We need to see some consistency in the estimations of the two approaches. And we can assess the uncertainty for this case based on the variability on the ratios. If these ratios are quite similar from different years, we expect a small uncertainty associated to this splicing technique. The larger the variability in the ratios, the larger the uncertainty we may expect for the estimations for those data. So that's how we may account for the uncertainty. We may calculate the ratios, we may calculate the standard deviation of the ratios, the variability, and we can apply this statistical technique for assessing the variability and deriving an uncertainty of value for the estimations. Of course, we have to expect higher uncertainties for this type of estimations because we naturally have uncertainty on the estimations when we have the data. If we do not have the data and we have to estimate it, we are introducing an additional uncertainty for this technique. So the uncertainty associated to all these techniques in general are higher than the uncertainty associated to the original data sets. I see a few questions. Should we use the average difference between the two tiers instead of the average of ratios between the two tiers showed here for the OLAP? Not sure if I understand. I think I understand you are saying the same, like, should we use the average difference? The difference of the ratio. Well, I think it's pretty much the same because the difference, in reality, the difference is affected by the magnitude of the emissions. So what we really need, what it's more representative is expressing the difference, but not as the difference itself, not one tier, not the difference between the two tiers, but the ratios between tiers. That's a more appropriate way of linking the two of them. Because if the difference in the estimations is not so high, there may be no problem. But if the differences are quite high, the length of the gray bar may vary a lot between one year and the other. So we will be introducing some variability that is not related to the series itself, but it's to the magnitude of the values. So it's better if you use the ratios here for linking the two of them. When is it recommended to adjust the early years of the inventory? For example, changing from tier 1 to tier 2. When it's recommended, well, it's recommended once we move to tier 2. Of course, if you just have one new inventory year applying tier 2, it's very different. It's very difficult. Not difficult in the sense you could apply just the ratio, calculate the ratio for that year and apply it to the previous data. But you have no idea of the uncertainty of that because you don't know, you cannot assess the consistency between the two approaches. So at least I would say like 3 years may be a good point, but that's totally up to each case. You may know a lot better the estimates, the categories, so you may be able to better assess how many years you need of overlapping data, if that's the question. So you start applying this technique and fill all the rest of the series applying the new tier. But I would say at least 3 years sounds like a reasonable number. You may apply it with 2 years. If you see that the two ratios are quite similar, it may be an indication that it's working good. But the more data you have, the better assessment you can apply to this. Could you give an example of how to calculate the uncertainty of this splicing technique? Yes, it's that what I said before. We can assess the variability. We calculate the ratios. We calculate the average of the ratios. We can calculate the standard deviation of the ratios. And we can use that to derive the uncertainty. If we see that the standard deviation of these ratios are, 10% from the mean, we can assess if the variability or if each individual variability. So based on that, we may calculate the differences in each of them and have an average of the differences in relative terms, applying the standard deviation of it, calculating the standard error, the same techniques we saw during the first days of the webinars, like applying a statistical analysis, typically calculating the standard deviation and seeing how far the standard deviation is in relation to the mean value. In this case, we would apply this standard deviation and we will transform this into a 95% confidence interval by multiplying by 2 around. So the second technique, and it's one of the most commonly used, I would say, most of you may have already know about this technique. It's very common. It's probably most of you studied this at the university, regression analysis. If you had statistics in the university, you probably studied how to apply a regression analysis. And that's the idea of this technique. It's just to derive the information from one variable based on the information of another variable that we have control, that we know that we have good information, and we know that it's a very good driver of the dependent variable. So we will have an independent variable that we know, and we will estimate the dependent variable which we do not know, or we do not have enough information. It's kind of similar to overlapping, but instead of using just the ratios, we use the equation, the regression equation of the assessment. So there are a lot of it's a whole world how to apply our regression analysis. There are a lot of things to consider. The idea of today is it's not to learn how to apply our regression analysis in detail. We will see a few cases. We will see how to apply it in an Excel, but not in great detail. But you have to understand that the regression analysis you may apply a simple regression, multiple regression, several variables that are combined to derive the value of the dependent variable. The regression, the relationship, as we saw yesterday, may be linear, but it may also be non-linear. So we have to study a little the behavior of the variables we want to assess, to understand how to apply this regression analysis, the surrogate technique. So what we really need is to identify the dependent and the independent variables, and to understand how they correlate, the dependency, the correlation coefficient. We need to understand the correlation between the two variables, and then we can run the regression analysis, the regression line. And for deriving the uncertainty of this type of techniques, this is a statistical technique, we can apply the standard error of the regression. So from that, we can apply the regression analysis. We obtain the formula that links one variable with the other. And with the statistical analysis, we will see how to do that in Excel. We can calculate the standard error of the regression and use it as a proxy to derive the uncertainty associated to this regression analysis. This is one way. There are several ways. When we are dealing with statistics techniques, there are several different ways to assess the uncertainty associated with it. Using the standard error is one of the most common ones, but there are several others that could be used. The other technique is interpolation. This is quite, I would say, in my experience, I've always had to apply an interpolation in accounting the GHG inventories. I don't remember a case where I didn't have to apply interpolation to fill the data, some data gaps in the data we require for assessing, for calculating the emissions, the national GHG inventory. So it's a very, very common technique. There are several ways to do interpolation, and again, you can have a linear interpolation. You may have a quadratic interpolation, a cubic interpolation. The good practice says don't go too high in the power of the extrapolation, because it's true that higher powers interpolation, like a cubic interpolation, may fit better the data. But if you just start adding fourth, fifth level of interpolation, the reality may not be such, and you may be introducing variability. A polynomial of a power of 5 have a lot of variability, so it's not good practice. In general, you may use linear interpolation or a quadratic interpolation in some cases where you see that the trend or the behavior of data series, it's not so straight, it's not aligned, it's not fitting well with a linear interpolation. You may use a quadratic one, or even a cubic one in some particular cases, but not more than that in general. I see a questions. Please, may you come back on the explanation of situation in which we can use surrogate technique with an example. We will apply an example in Excel, so I will hold that question for the moment we switch to Excel, and we can apply the surrogate data with the example in particular. Just for the sake of time, we will go through the 4 techniques, and then we will do some hands-on exercises. So interpolation, basically, it's very useful to fill some data gaps that are between other data which we know. You can apply it for several data in a row, like the one that is shown here. We have here 4 missing data, so we can apply interpolation for all of them, or we may have some data gaps distributed there, so you can apply it intermittently as necessary. What's required here is it's kind of smooth or stable trend we see, or if not stable, at least we identify. If it's not linear, at least we are able to identify if it's kind of parabolic or something like that. But we need to see a quite clear trend of the data, so we are pretty confident that the interpolation and the interpolated value you get, it's fair of the real behavior for those years or months or wherever data gaps we have. If we don't see a clear trend and it's very variable and we can really identify a linear relationship or a quadratic or something like that, if we don't see clearly that, perhaps it's better to move to surrogate and find another variable that explains the behavior of this one. And we can assess variability. The assessment of the uncertainty of the extrapolated data could be done by assessing the variability of the data series we have. That's one way we could do that. We can also identify another technique that it's a little more sophisticated. It's not really, it's not difficult. It's pretty simple, but we could apply a linear interpolation and assess the uncertainty of it by comparing it with a quadratic interpolation. So the differences between the 2 approaches to interpolate the data gaps may give us an idea of the uncertainty associated with the linear one. So you expect a quadratic interpolation to better fit the data than a linear interpolation. So this is another way we can assess the uncertainty. Again, there are several ways of assessing uncertainty for these statistical techniques. Good practice is to, if you are confident with your knowledge of statistics, you can assess it on your own, or you may ask someone in the team with statistical background to help you apply this technique and assess the uncertainties associated to these techniques. Another question, if we have data from, for instance, 2014 to 2020, and we have no data for the years before 2014, what's the best technique to calculate data for those years? You may use, depending on the type of data we are talking to, depending if it's activity data, depending if it's estimation of emissions, but in general, you may use either overlap if you have the same data for 2014 to 2020 from 2 different sources, and you have access to previous data in one source and not for the other, so you can use the overlap technique. If not, you can try to apply the surrogate technique, so identifying an independent variable that is linked to the data you have, so you can apply a regression about that. But in general, what you are suggesting here, if you have just data for a period and not for previous, you'd be in a case of extrapolation there. Because extrapolation really means, and that's a good way of moving to the next slide, extrapolation means that you do an assessment of a data series, and then you estimate something that is outside the boundaries you've used for the estimation, that you've used for the assessment. So that's extrapolation. And that definition covers moving for future years when you don't have data yet based on previous years, but also means moving to previous years based on data on most recent years. In both cases, we would be extrapolating the data. We would be using data from a period where we know, and we will be estimating data that it's beyond that range, either in the future or in the past. Both cases are extrapolation. And that's how extrapolation works. You may have data unavailable for the last year or for first year, previous years. So there are several ways to extrapolate data. You may, if you see a very stable trend, you may just apply an extrapolation technique that is based on following the trend you see, the trend you are observing. You may just follow the trend, like here. Imagine this last point. If you are in year 2000 and you see that it's a very stable trend, the most natural extrapolation technique would be just to keep the same trend and estimate this next data point based on the trend. If we do not see a stable trend, we may extrapolate, but not based on the trend, but based on surrogate technique. We may try to find some, again, dependent or the independent variable that may be linked to this data series, and we may create a regression analysis. We get the formula for that regression analysis, and we apply that formula beyond the interval we used for deriving the formula. That would be extrapolating, but based not on the trend, but on a regression analysis. That's useful when we don't see a very clear, stable trend. The problem with extrapolation, as I mentioned, is that we are guessing informations and values that are outside the region where we have information. And that may be problematic because if some important changes happen for those periods, we have no way of knowing that. I mean, if we have a way to understand that something really fundamental change, we may be able to adjust an extrapolation and account for this factor. But if we don't know that, and we just based the future behavior based on the observed past behavior, we run the risk of estimating something that it's not realistic. So extrapolation, it's good, but we need to be careful with it, and it's not good practice to extrapolate too much. 1 year may be good, 2 years may be good depending on the observed trend or something like that. For longer term, it's not so good to use an extrapolation technique. It shouldn't be our first choice to do that. If we have no other choice, well, we have that technique, but we have to understand the uncertainty associated to that may be very high. It's quite similar to interpolation, but the problem is that in interpolation, we are inferring some values in a region where we have a lot of information. On the contrary, when we extrapolate a value, we are guessing something that's outside the region we know. So that's the problem. And statistically, when we interpolate the errors, the uncertainty is limited. It may be high, but it's limited. When we extrapolate, the uncertainty is not limited. It may tend to infinite. So that's the risk of extrapolation. And that's why extrapolating it so much is not for a long period, it's not good practice. But the good thing of extrapolation, if we are getting estimates future years, is that we may have a point of control when the data for those years becomes available. That's very, very important. It's a great help for us to understand if the extrapolation we used was good, if the assessment of the uncertainty we applied at the time was representative of the reality, and that helps us create better models for the future. If we run some similar problem in the future, we may have better information now to do a better extrapolation and to assess the uncertainty better. So let's quickly move to the hands-on exercises here. Not sure if we will have time to do all of them in detail. I have 3 of them for surrogate, interpolation, and extrapolation. I will switch. I will stop sharing the screen. And I will share the Excel file. Where we will do the exercise. If you have it open, if not, please open the Excel file. Let me know when you're seeing the Excel.
Yeah, Diego, you can see your screen.
Great. I will just zoom a little. I hope that's enough. So if you go to the surrogate tab, you will see a series of data for cement production and lime production. And you see that we don't have data for 2 years, the last 2 years, for the lime data series. So we will try to apply the surrogate technique. Particularly, we will apply a regression analysis here. So one thing we naturally do, and it's the overlap technique, is just calculate the ratios here. How much lime related to the cement production to see if we observed some trend. So if we do that, we see here a quite stable trend. So in this case, we could apply an overlap technique to derive these two cells that are yellow shaded here for year 15 and 16. So we could apply an overlap technique here. We will not do that. We will apply a regression analysis. And that may be done very simple. If you have the Excel where we've seen, I don't remember if yesterday or the day before, if you go to Data tab and you have the Data Analysis tool, you may just easily perform a regression analysis with these two variables. So let's first create a graph. What happens if we visualize the data? So if we include a graph here, we will just create a graph for the two variables. It's good practice to include some graphs to see how they behave and how they relate. I will create another graph for the correlation. So I just graph one variable versus the other. That may be more useful for us. So this chart shows the relationship between the two variables. The cement production, the vertical axis, and the lime production in the horizontal axis. And we see here that there is a very clear correlation between the two variables. The two values are clearly correlated, highly correlated. We could add the trend line in Excel to see the correlation. We see a linear correlation. We may select to display the equation and the R square of the regression. It's a very simple way of trying to assess if the variables are correlated and the level of correlation. So we see here this. We see that there is a high level of correlation. The R square is 0.94, is very high, it's very good. And we have an equation here. We already have here the equation that links the two of the parameters. Just let me, I will just remove this because I would like to plot it the other way. I would like, since I want to estimate the lime production based on the cement production, I want the axis to display in the other direction. So I will just change that. And I will switch the data. So now we have in the vertical axis the lime production, and in the horizontal axis the cement production. And we have here the regression equation and the coefficient, the R square of the regression. So with just doing that, what we just did is the regression of the two variables. So we could just calculate the two missing values by applying the formula we have there, like 0.2798 times the amount of cement plus 21, 25, 27. I'm just applying the formula, the regression formula, and we just filled the data gaps for this case. That's pretty simple. We'll go to the chat in case there are some questions. There are several. Can you explain the difference between interpolation and extrapolation? I'm not sure if that question was before or after I explained it, but never mind. Interpolation is when we estimate a value that is contained the range of values we have. That's interpolation. Extrapolation is when we estimate a value that is outside the boundary of the values we are using. That's the difference between interpolation and extrapolation. There are some GIS tools or softwares that can be used for interpolation and extrapolation, for instance, with inverse distance weighting algorithm in ArcGIS. Do you recommend such approach? There are definitely a lot of softwares that can be used to apply these techniques, or others even. There are a lot of techniques. There are not any of these four techniques. So in reality, there is not just one suggestion that may fit all. It's depending on the case, depending on the information you have, depending on the access you have to different softwares. You may assess on your own the one that you feel more comfortable with, not only for the data, but for the use. Because if you have a great software that it's very difficult to use, you're having to put a lot of effort to learn how to use it. It's not you're not feeling confident using it. Perhaps it's better to move to another one that you feel more comfortable. So at least until you get used to, or you need further improvement to that. If you have data for 1995 to 2000, and then you have data for 2005 to 2020. In between data, do you have, this is interpolation? Yes. If you have data from previous years and for future years, in between, if you use all the data you have, you will be interpolating. If you use just a portion of the data to estimate the future, or the other portion of the data to estimate the past, you would be extrapolating. If you use the entire set of data, you will be interpolating. Again, if the data points are for a long period with missing data at a few points, can we use extrapolation for that analysis? That depends on where the missing data is. If it's in between the data points, you are interpolating. If it's beyond the data points you already have, it's extrapolation. In case I'm using Greenhouse, but for interpolation, we can intersect equation and R square in the graph to see strengths of I see a few comments. Can't see the screen. I guess that may be a problem of you in particular. You may try to switch the view in your screens. So we have 20 minutes left for today. So I'll just go back a little to the Excel to complete the exercise. Something I wanted to show that may be used to easily calculate or estimate the uncertainty. I will just move this graph here. We'll delete this one, just keep this other one. If you go to Data tab in your Excel, and you have this data analysis enabled, you may find several analysis tools. But one of them is regression. So you can easily apply a regression here with all the associated statistics. So I've already created the model here, but you may just select the independent variable. You select the dependent variable that you want to estimate. You select your confidence interval. I will not plot this. You will select here the output range so we can see it next to the data. And you just have all the regression model and the statistical analysis of the regression model available here. Let me put this graph a little smaller. So you could see here the R square, that's the same we obtained in the equation. We have the standard error. We have the analysis of variance with the regression, the residual, all the statistics. We have the assessment of the coefficients. You see here the coefficients are the same in the equation. This is the intercept coefficient. It's the one here, 21, 25, 27. It's this one. You will just remove the decimals. This is the coefficient. It's the same in the equation. 0.2798 is the same here. You have the standard error for each of the coefficient. You have several other values, the 95% confidence interval associated to each of the variables. You have the residuals here. The residuals are, if we apply this formula to the same data set we already have from year 1 until year 14, we will not get the same values for Lyme. We will get some approximation. This is the predicted values for the same data set we have. And this is the differences. The residuals are the difference between the predicted value and the values in the data set. So we can use this to estimate the variability of the results. But ultimately, and for the sake of time, what we could use here to estimate the uncertainty is to apply the standard error. You see here the standard error, and you can calculate how this standard error relates to the average values that are here. So we may calculate the relationship between the standard error relative to the average value used in the calculation. I misspell average, sorry. So you can see that the standard error for this regression analysis is around 7%. So if we apply a 95% confidence interval, we should multiply this for around 2. So we may confidently say that the uncertainty estimate, the uncertainty associated to these two estimates of the lime production for these 2 years may be around 14% or 15% if we round it up just. So that's how we can apply a surrogate technique and derive the associated uncertainty. I will quickly move to the interpolation, extrapolation sheet, just to quickly show how we can derive the uncertainty, how we can apply it. It's basically pretty much the same. We can calculate. In this case, you see, it's coming from a census. We have information from censuses and the population, and we have, of course, we do not perform censuses every year, so we have the data every 10 years, at least in some, it's a typical situation in developing countries. So if we need to fill these data gaps, we may apply an interpolation technique. So we may, if we apply a linear interpolation here, we may just have the two last values, and we may just calculate the ratio of it. We may just do the difference in the data, and we may divide it by the number of years we have. So this data, this value is the rate, the increase, how many individual, how the population grows every year. So if we just add the last value to this one, we get an approximation of the population for this year. In this case, for population, in general, the national statistics already provides these interpolation values, so you better use those. But if you want to apply it on your own, you can do this. I will just make these values to remain, so I'm able to extend this extrapolation. And what we see here is now we apply the interpolation technique to propagate this. I will not do the extrapolation, but it's pretty much the same. The difference is that we are using the equation to estimate data on for the future. So I will go back to the presentation. You will stop sharing the screen here. I will share the presentation again. So we have 10 minutes left. So on the surrogate, what we were able to see is how to apply this technique and how to derive the uncertainty associated with this. Something similar can be done for interpolation. We can interpolate the values. If we extrapolate the values, again, we can apply the same formula, the same type of either following the tendency or applying the regression line for the values and the years. And if when the data, new data is available, here, I don't know if you see, but there is an orange X there. That's when data from the new census becomes available. We can compare the estimation we did with the data from the previous census. And we are able now to understand the uncertainty associated. Of course, it's ex post, but that helps us in future estimations if we used to use this technique again. So for the last 10 minutes, I would like to go through this expert judgment technique that may be very helpful for us to assess the uncertainty in a lot of cases where we don't have data. So the key goal for expert judgment is to understand the variability, the intervals where the variables may be, so we can assess the uncertainty or develop an appropriate probability density function. So we are interested not in knowing the value of one variable, but to understanding the variability that may have this variable associated. So when we don't have relevant empirical data, when we don't have measurement, we don't have national statistics, we don't have papers or data where we can do statistical analysis, we may go to experts and ask for their opinion. And there are formal elicitation protocols that we may follow, and it's very important if we go and consult the expert and follow the solicitation protocol to document all the process, so we are complying with the transparency, with being transparent on how we obtain the information, where the information came from, and how we apply it in our national GAG inventories. I will not go a lot in detail here, but it's very important to set the picture clearly to the expert, to explain the problem, to explain the purpose, why we need this information, what we will use this information for, to clearly explain the procedures, trying to ask the expert to think of previous experiences that may be similar to the ones we want to assess, and to capture the data from each of the experts. And it's good practice to perform some verification just to ask a different expert the outcome of the result and see if the expert feels comfortable, he or she feels comfortable with the data, with the results, to test outliers and any problem that any bias the data may have. There are some typical problems associated with expert judgment. For reference, you may go to the Annex 2A.1 from Volume 1, Chapter 2, where these elicitation protocols are described in detail, and you may see there the typical problems that appear when we use these elicitation protocols. But in general, we have 4 approaches to get data. We may ask the expert a value. We may give the expert a value and ask the expert opinion on the probability of that value to happen. Or we may tell the probability and ask the expert his or her opinion on which is the value that may be associated to this probability. We may ask the expert to tell us intervals, the interval methods, we may ask the expert to tell us an interval that the expert consider represents half of the values. So there are different techniques we may follow. I will just put all of them here. And I just use the last 5 minutes to go through them. For instance, the fixed value, we may ask the expert to tell us what's the probability he or she thinks for an emission factor would be less than 100, for instance. So we will get an idea, a sense of the probability of these values, and we repeat this for different values. So we create like a map of the probabilities and values to derive a potential probability density function. Or similar to this one is that we may ask an expert what will be an emission factor, such as there is only 2.5% probabilities that the emission factor be lower or higher than that. So we are asking for values instead of probabilities and testing these intervals, again, to create a map of the variability and the probability of different values to happen according to the expert experience. And we repeat that with different experts. So we create different estimations and we are able to build some kind of probability density function. We try to quantify the information that is subjective to each expert experience in particular. The interval method is just trying to identify the mean value, the quarter values of the intervals. So you choose a value of the emission factor. You ask the expert to choose a value that it's the most likely value, that half or that leaves 50% probability of values to be higher or 50% probabilities of the values to be lower. So we have that point, and then we repeat that process to divide again each of those half intervals into halves again, and you get the quartiles, the 25% probabilities each. So again, you are repeating this process with different probabilities and intervals with different experts to create a potential probability density function. Or you may ask the expert to create a graph on their own on how they feel a probability density function may look like for a particular variable. So with that, we reach the end of the webinar. I see there are a lot some questions in the chat. I think we have just a couple of minutes. I will try to go quickly through them. How did you obtain the statistical information? I think that was referring to the regression analysis. I can share the spreadsheet with all the assessment for you to follow offline after the webinar, if that's helpful. So perhaps you can just follow the Excel and understand how that happened, or you can review the recording. Since R square is very strong, can we use the two missing values as relatively good values? Yes, the correlation is very strong, but if we apply the statistical analysis, we should apply this uncertainty assessment, that there are different techniques and you may assess on your specific knowledge of the sector which one may be a better fit to your case. Yeah, sorry for it's too fast to follow. Yes, I imagine it's difficult to follow the presentation and the Excel, and do your own calculation. Sorry about that. You may have some time to follow the Excel on your own. If you have questions, you may just send emails after the webinar, and we may follow up with specific questions after. It's possible to use data from population to improve the estimations. It depends on each category, the type of information you are using. If that helps, you can use those values. From the extrapolation of time series, can ARIMA models be used? Sorry, I'm not familiar with that models. Maybe there may be some other experts in the webinar that can help you with that question. I have data coming in from different powerhouses, diesel consumption. I'm using the default emission factor from IPCC. Do I calculate the uncertainty for each individual powerhouse? You can if you have the data, or you can aggregate all of the data and try to assess the uncertainty in another level of aggregation. So that's your choice. You will have to choose which one and assess the uncertainty for the case you choose. Okay, there are several others. We don't have time yet to go through all of them, so I will stop here. Thank you very much once again. It was my pleasure to be here with you during this week. I hope you enjoy it. You don't get too bored, and you get something new after this intense week of webinar. Thank you very much, and back to you, Seven.
Thank you very much, Diego. With that, we conclude the technical part of the webinar. And I see people are very happy. They are clapping. Thank you very much. We are also happy because we've been able to cover all the agenda items. And we've also noted very good participation. In terms of participation, we saw the first day more than 450 participants, and then on average 350 participants per day. So I think the level of participation for us is very good. We've also noted the quality of the technical content of your interventions. So we saw the question in the chat; they have good quality. So all these observations demonstrate your interest in the topic, and we sincerely thank you for the interest. We plan to repeat this webinar between September, October this year, and we will keep you informed. But in the meantime, please apply the knowledge gained in this webinar. When preparing your first BTR or maybe your last BUR, and then get back to us if you have any questions or any challenges. On Monday, I mentioned our platform, GAG Help Desk, that you can use to pose any questions when preparing your national inventory report. Early next week, you will have access to all materials using the link that we've shared with you previously. You will see there all the presentations, the spreadsheets that we get from Diego, and also the recordings. So you will have all these materials early next week. We also need your feedback to identify where we need to improve. So if you check your email, you will see a link to a SurveyMonkey, and we will be very, very happy to receive your feedback. And thank you very much for in advance for providing your feedback. In terms of announcements, we have in our calendar a webinar on soil organic carbon to support national GHG inventories from developing countries under the ETF of the Paris Agreement. The webinar is scheduled to take place from 16 to 18 April, so this year, and to be in English, French, and Spanish, like this webinar on uncertainty analysis. We have supported the development of a tool, a mitigation tool, and also a data collection and management tool. A webinar on the mitigation tool will be organized in April, also in English, in French, and Spanish. That you can find all this information in our webpage. We will launch the call for nomination to participate in all these webinars. I mean, the soil organic carbon webinar and mitigation tool early March, but we will keep you informed. So finally, I would like to express our gratitude to Diego. Thank you very much for sharing your expertise, for preparing the materials and delivering the webinar. Thank you very much for your collaboration. Also, our gratitude to interpreters. Thank you very much. You've done a great job. And I also thank all my colleagues from the Secretariat for the support. And on behalf of the UNFCCC Secretariat, I sincerely thank all the participants for your active participation. Having said that, the webinar is now closed. Thank you very much once again, and enjoy your weekend. Thank you. Bye-bye.